3 Atlas appears to be executing a maneuver that no natural object should be capable of, slowing as it nears Jupiter with a level of accuracy that feels almost purposeful. The object is closing in on the edge of Jupiter's Hill sphere, the narrow boundary where the planet's gravity begins to give way to the sun's influence. And the placement is so exact that it feels less like chance and more like an intentional pause that an unknown comet has ever displayed behavior this precise, and the moment has sparked new questions about what could be directing its movement. If this is not a natural trajectory, then what is shaping what comes next? The journey of 3 Atlas through the solar system has become one of the strangest stories in modern astronomy, and its approach toward Jupiter began long before anyone noticed something unusual in its motion. The object first emerged as a faint point of light arriving from deep interstellar space. At that stage, it followed a standard hyperbolic path, exactly what scientists expect from a visitor not born within our system. Its speed, heading, and form all appeared ordinary. Because of this, researchers assumed they were watching another rare traveler that would pass through and depart without incident. That assumption began to change once the object moved closer to the sun. A slow but noticeable shift in behavior appeared, and that subtle change now sits at the center of the debate over whether the object is responding to external forces or actively adjusting itself. The mystery deepens when we examine how 3 Atlas reacted to sunlight, because the object exhibited a non-gravitational acceleration immediately after passing perihelion, the point of closest approach to the sun. This acceleration nudged it slightly away from its original course. While the force itself was weak, the direction of the push was almost perfectly aligned with the path needed to guide the object toward where it is now headed. Scientists are familiar with comets changing speed due to jets of gas released by heating. However, those jets usually act in chaotic or uneven ways. Most comets spin, tumble, and wobble as they warm, and their tiny thrusts produce irregular motion that rarely forms a clean trajectory. Atlas behaved differently. And that difference has led many astronomers to believe the object is not simply drifting, but may be influenced by internal forces or structural properties that remain poorly understood. Another key detail is that this deviation was recorded by more than 200 observatories worldwide, with each new observation reinforcing the same conclusion. The object was no longer traveling along a path explained by gravity alone, and every refined model showed an increasing alignment between its new route and the boundary of Jupiter's Hill sphere. This level of consistency across global data sets makes the change in direction difficult to ignore, especially since the acceleration shifted Atlas by exactly the amount needed to reach its present target. The cause could still be natural, but the precise combination of timing, angle, and magnitude has kept the scientific community deeply engaged in trying to understand what is actually occurring. What makes the story even more unexpected is that Atlas showed no major signs of instability or fragmentation as it moved inward, something many interstellar objects display under intense heating. Rather than breaking apart, it became more stable and continued forward with smooth, controlled motion. This calm behavior strengthened the idea that the object may possess an unusual structure or chemistry that allows it to remain intact under extreme radiation. When all these details are connected, it becomes clear that the current maneuver near Jupiter is not a sudden event, but the outcome of a long sequence of small, precise adjustments that began months earlier near the Sun. The pattern raises a serious question about what kinds of forces can sustain such a consistent and finely aligned journey. If this motion resulted from random outgassing, why did it produce such a clean direction toward a single point in space? And if it was not random, then what mechanism could guide an interstellar object with such accuracy? These questions lead directly into the next phase of the story, because the answer may be hidden in the extreme precision defining Atlas's current approach. The extraordinary accuracy of 3 Atlas's present path is the most startling aspect of the entire event. And the numbers behind that alignment reveal just how unusual the situation really is. The object is expected to pass Jupiter at a distance of about 33.2424 million miles. Yet recent measurements indicate it will arrive only about 35,000 miles from the exact boundary where Jupiter's pull balances the Sun's. That places the error at 1 part in 26,000, a level of precision rarely achieved even in carefully planned space missions. To grasp how strange this is, imagine throwing a needle from Los Angeles and having it land precisely on the edge of a coin in New York. Precision like this almost never appears in natural motion, especially for an object that has crossed billions of miles of open space. The significance becomes clearer when we consider how interstellar objects usually behave. They typically enter the solar system with unpredictable rotations and uneven surfaces that respond differently to sunlight. Minor variations in heating can push them in multiple directions, making their final paths difficult to forecast. Even with advanced models, astronomers normally expect a wide spread of possible outcomes. Atlas has defied that expectation, with each update narrowing the margin of error instead of expanding it. This increasing accuracy is more than a scientific curiosity, because it suggests the object is following a clean, stable line that does not resemble the noisy pattern seen in natural comet motion. The data also show that this precise approach did not develop slowly over many months, but emerged sharply after the object passed close to the Sun. The slight acceleration that altered its course produced exactly the correction needed to guide it into the narrow zone surrounding Jupiter's Hill sphere. Had that acceleration been even slightly stronger or weaker, the object would have missed the boundary by millions of miles. The probability of a natural push occurring with precisely the right strength and direction is extremely small. And this is why many researchers are questioning whether simple physics alone can explain the motion. The effect resembles a final steering correction used in spacecraft navigation rather than a random release of gas. The alignment itself matters because the Hill sphere is not a destination natural objects typically approach so closely. When comets pass near Jupiter, they're usually pulled inward or pushed away, rarely lingering near the outer edge. The fact that Atlas is not plunging into Jupiter's stronger gravity, but instead sliding along the boundary, makes the movement appear even more intentional in many respects. It resembles a controlled approach that ends where gravitational forces nearly cancel out. A situation more familiar in planned missions than in drifting debris. When the tiny error margin, the sharp correction near the Sun, and the unusual target are considered together, it becomes clear this is not a standard trajectory. Something is holding the object on a path that matches a single mathematical line across millions of miles of space. If this were coincidence, it would rank among the rarest ever observed in astronomy. If it is not coincidence, then a more pressing question follows. What kind of process can guide an interstellar object with such precise timing and accuracy? Jupiter's Hill sphere is one of the most significant gravitational structures in the solar system, and understanding its role helps explain why Atlas's behavior stands out. The Hill sphere defines the region where a planet's gravity becomes stronger than the pull of the Sun. For Jupiter, this region extends tens of millions of miles. Most natural objects never intersect this boundary because their paths are shaped by chaotic forces such as solar radiation, collisions, or uneven outgassing. They either fall deeper into Jupiter's pull or remain well outside its influence. As a result, the boundary functions more like a mathematical threshold than a physical destination. Since objects do not normally aim for this thin transition zone, Atlas's precise approach is already remarkable. This boundary is also unusual because the forces inside it behave very differently from those outside. Once an object crosses into the Hill sphere, Jupiter's gravity begins to dominate, allowing the object to be captured or accelerated. Remaining outside keeps the Sun in control, producing motion that is more stable and predictable. The line separating these two regimes is delicate, where even a small change in speed or direction can lead to two entirely different futures. Because of this sensitivity, it is extremely rare for any comet to match the exact distance where these gravitational forces balance. The boundary is not a place where natural bodies pause, slow, or carefully adjust their course. The contrast becomes clearer when we look at how space agencies use gravity. Engineers designed spacecraft trajectories to exploit deep gravitational wells like Jupiter's for slingshot maneuvers. These maneuvers demand precise timing and alignment, because even a minor error can place a spacecraft on a vastly different path. Missing the edge of the Hill sphere by just a few thousand miles can translate into millions of miles of deviation later on. Reaching this boundary with exact accuracy is difficult even for human technology. Seeing an interstellar object display similar precision raises serious questions about the forces acting upon it. Another striking detail is how narrow this transition region actually is. Although the Hill sphere itself is enormous, the precise boundary, where control shifts from Jupiter to the Sun, is extremely thin relative to the surrounding space. Striking that exact line is like landing on the edge of a moving shadow, since its position shifts slightly with each orbit. This makes Atlas's alignment even harder to attribute to chance. The more it is studied, the clearer it becomes that the approach is too clean and too steady for a natural body that has wandered for millions of years through unknown environments. All of this leads to a difficult question. If the Hill sphere is not a place objects naturally seek out or stop, why is Atlas positioning itself so perfectly along this invisible line? The idea of a precision parking maneuver becomes easier to grasp when we examine how Atlas altered its direction after passing the Sun, because that small change mirrors what a controlled adjustment would look like during a space mission. The object received a gentle push that shifted it away from its earlier path, and the magnitude of that push was almost exactly what was needed to guide it toward the edge of Jupiter's Hill sphere. Natural comets do experience minor forces from gas jets as their surfaces heat. However, those jets act irregularly and typically send objects in a messy, unpredictable motion. Atlas has not exhibited that chaos. Instead, it has remained on a steady line that continues to match new predictions with surprising accuracy. One reason the shift feels intentional is its timing. A correction made much earlier or later would not have delivered Atlas to the narrow boundary it is approaching now. Timing matters because the solar system is filled with moving bodies, changing sunlight, and competing forces that constantly threaten to push objects off course. Most cometary jets erupt in bursts, and those bursts usually cancel one another out rather than produce a clean vector. If Atlas behaved like a typical comet, its trajectory would have drifted millions of miles away from the region it is now nearing. Instead, the push it received resulted in a clean adjustment, placing on a path that aligns with a single mathematical point in space. The motion becomes even more intriguing when compared with standard navigation techniques used in human spaceflight. Spacecraft aiming for small or sensitive targets often perform late course corrections after passing a massive object like the Sun. These adjustments fine-tune the route using minimal energy. Atlas fits this pattern, having altered its path after passing perihelion and then holding that corrected line with almost no drift. The way it maintains this trajectory gives the impression of a system responding to gravitational forces in a controlled manner. That is why some researchers describe it as behaving more like a probe than a simple rock. The destination itself strengthens the idea of a maneuver, because the outer edge of Jupiter's Hill sphere is a region where tiny forces can produce major effects. It is a zone where Jupiter's gravity competes directly with the Sun's, making it a sensitive area where objects can slow or change behavior. A natural comet would usually be pulled inward or pushed outward long before reaching this region. Yet Atlas is gliding along the boundary with unexpected stability. That stability supports the notion that the object may have physical properties allowing it to remain balanced in ways most comets cannot. When these elements are combined, the picture grows more mysterious. The shift near the Sun, the stable path, and the unusual target all resemble the outcome of a carefully executed adjustment. If this were accidental, the odds of everything lining up so perfectly would be extraordinarily small. If it was not accidental, then a more serious question emerges. What internal process could produce a maneuver that looks so much like deliberate action? The question of what is guiding Atlas becomes even more complex when we consider the four main explanations scientists have proposed, each attempting to account for a situation with almost no precedent in known astronomy. The most conservative explanation suggests the trajectory might result from observational error, since early measurements of fast-moving objects can contain small inaccuracies. However, more than 230 observatories have now tracked Atlas, and each new dataset has confirmed the same path with shrinking uncertainty. This level of agreement makes the error explanation increasingly difficult to support, especially as the object continues to meet predictions with remarkable precision. That a second possibility is that Atlas is being pushed by outgassing in a rare but natural configuration. Heating can trigger repeated gas jets that gently move a comet in one direction.